promised to fill in some gaps in the proof of the Furstenberg's theorem, and I will, but I also want to state the theorem which Furstenberg himself considered as his theorem. And to do that, I need to do the following thing. I first of all have to introduce some invariant measure of a certain Markov chain. Now, the purpose of this is the following. And we have this Lyapunov exponent, which can be simply defined like that due to, well, this is by definition can be considered as the limit 1 over n log of the norm of A of n, where A of n is an and so on a1, the product of these matrices, and aj, they are IID. Or actually, for this purpose, we don't need them to be IIDs, and can be simply a sequence of stationary matrices aj of omega. There is always an omega hidden there, is a matrix valued function defined t to the power j, well, j minus 1, if I start with 1, yes. Of omega. But there is a very reasonable and natural question: can we actually find the number? What is the way in which this number can be found? And this is given by, the answer is given by the so-called Furstenberg's formula. And this is what I also want to explain. Because one thing is the existence. The other thing is it positive or not? It can be, it is always non-negative, of course. And the final thing is, can we actually somehow evaluate it? Is there a reasonable way to find it? And there is a very reasonable way to find it. And the remarkable fact is that the formula, which of course is well known, does not prove, you cannot extract from the formula that this number is positive under the same conditions. Okay. So how do you, what is the other way, I would say, to control this quantity? In fact, well, as I said already a couple of times, all of that is possible due to the Kingman's subadditive ergodic theory. You can say this will be the definition, but it doesn't help if you don't know the Kingman's subadditive ergodic theorem, because you never know whether this limit exists, and it exists due to this theorem, right? But there is a very different way. And this is where the whole story started, when Furstenberg and Kesten and then Furstenberg on his own were developing this theory. Let us consider the following transformation of a unit sphere. If you have a vector x belonging to a unit sphere, I will write it like this. norm of x is equal to 1. So S is in Rm. This is a unit sphere. And if we have a matrix A, then it acts on a unit sphere in this way. X is mapped into Ax divided by the norm of Ax, so that to preserve the norm of the vector. If I have a sequence of matrices, I can consider the following sequence of vectors. So define, let me write it there. Define the following sequence of vectors. X1 is given, and then it is mapped into A1, X1 divided by the norm of A2, A1, X1, which is by definition X2, and this is mapped into A2, X2 divided by the norm of A2, X2, and so on. And you have so xn plus 1, which is an xn divided by the norm of an xn. And note the following thing, that if Aj are independent then x1, xn, and so on is a Markov chain. Markov chain. It's a Markov chain simply because the distribution of the next guy doesn't depend on one, depends only on two things, obviously, because simply because it is defined like that, right? That you can see it from here. That xn plus 1 is defined only by xn. Once you know xn, you know the distribution of xn plus 1. Because the distribution of the matrices an doesn't depend on anything. They are independent. So it's a Markov chain, always. Now, if they are not just independent, but also identically distributed, then it is a homogeneous Markov chain. So this Markov chain has an invariant measure, of course, or stationary measure. Sometimes both terms are used, and it depends on, Markov here. What does this chain have to do with what I have explained there? You see, if you look carefully at what I have written there, you will see that xn plus 1 is actually the following thing. It is a of n, not an, but a of n, x1 divided by the norm, n x1. So in fact, this is what is happening, because every time, if you do it for the second step, you will see that all these guys disappear. What is left is this thing. So this is the one first remark. Let's put it like this. Two. A very important thing is that in terms of this Markov chain, you can express this product. In fact, due to this formula, not the norm of A of n, which is here, but the norm of A of n applied to x. Norm A of n x1 can be written as follows. It is the norm of A of an x n minus or xn, yeah, times norm A of n minus 1 x1. You can easily see it simply because of this formula. What is xn? It is A n minus 1. A of n minus 1 x1 divided by the norm of A of n minus 1 x1. Now, if you use these relations, you will immediately see that this is what you have. Well, we can continue from here, and you will see that what I have is the following product. A n xn, the product. Well, the next one will be the norm of A n minus 1 xn minus 1, and so on. At the end, I will have norm A1 x1. Now we have a very nice function on a Markov chain, on a sequence, on a Markov sequence. If we take the log here, and this is what we want, essentially. You see, this quantity will behave, in fact, like this one most of the time for a typical x1. So the log of the norm of A of n x1 is the sum. You can easily check this identity simply by using the definition of xn, of xj. It's a very elementary identity, but a very important one. It will be the sum of the logs of the norm of A j xj. J from 1 to n. And of course, if I divide by n, and I divide by n here, it should converge according to the law of large numbers, or to the ergodic theorem, or whatever. because it is a stationary sequence once x1 is chosen randomly. So it will converge to the expectation, the log of the norm of AX. Expectation with respect to which measure? What is the measure I have to look at? How do I find this expectation? As I said, there is, I'll call this measure nu of dx, and mu is the measure on S such that mu of gamma for any gamma will be equal to the integral over S nu of ds well, of dx, say, right, times the probability that a x divided by the norm of ax belongs to gamma. This is a transitional canal, and this is the usual definition of the invariant measure of a Markov chain. You start with something. You can start with any point there, but you have to end up in a point which belongs to this thing. And this is the probability to do that. This is the probability of a transition from x to this point, and then you integrate over all x with respect to the same unknown at the moment measure. And then this is a stationary measure. Once you have chosen this measure in this way, you have a stationary sequence. In fact, a stationary pair. This measure, by the way, in the way I wrote it, it is independent of A. This is only possible because I said that the matrices are independent, statistically independent from each other. So this is why I can do it this way. If they are, then I have to put in a slightly more advanced measure. This is what Furstenberg and Kesten did in 1960. This is exactly their work. They looked at this thing in a stationary case, not in the case of independent matrices. And they invented this formula. In fact, it is known since then. I have not yet written the formula. Well, in an explicit form, it is here. But if you believe that for a typical, with respect to this measure, for a typical x, everything will converge to this gamma, I mean, here you will have the convergence to the gamma. Then the expectation of log of the norm of AX can be written in this form. It is the integral of this function with respect to its distribution, as usual thing. So it's a log of the norm of AX over, and here we have mu of dx mu, or d, yeah, mu of dA, where mu and nu are the distributions. And here I have this integral over this thing.
So, can I ask?
Yes, sure.
Make sure I understand. You proved this formula under the assumption that the matrices A1, A2, A sub 1, A sub 2 are independent. And there's a more complicated formula if they're stationary, generated by translating the omega by t's.
Yes. Then simply, instead of having a product here, I will have a measure nu of dx dA. I will have a joint measure, which will be invariant under the same translation. I don't want to go that far at the moment, but I'm just answering the question. So, and this is how it was done originally for a stationary case. So it's a very universal formula. I didn't essentially. Well, the only thing I would like to say, I have explained it. I haven't yet proved a very important moment here, a very important thing here, that indeed this number will be equal to what I want it to be equal to. This is a priori, in fact, not quite true, because maybe there are some measures here, nu, which are invariant, and, well, there are many questions here, you see. For instance, there is a question about the uniqueness of this measure. If there is a unique measure, then you certainly should believe that this is what is going to happen. But if it is not, then it is an unclear thing. I will now state the theorem, because so far I only explained how you will approach the theorem. And what Furstenberg in fact proved is the following thing. I have to introduce the following notion, first of all. I already said that there is this group G mu. G mu is the group generated by the support of mu. So I have, say, two matrices in the support with which but then I consider simply all products and inverses. So G mu is in fact a closure of G1 to the power plus minus 1 GS or GK to the power plus minus 1, where Gj belong to the support of mu. And I have to take the closure. So the definition, probably going back to Furstenberg, he was probably the first one who introduced this definition, is the following. A group well, I will stick to G mu, but in fact it applies to any group. G mu is strongly reducible. Strongly irreducible if no finite union of subspaces. When I say subspaces of Rn, I of course mean always linear subspaces of Rn is preserved by G mu. You see, it's a very important notion, so I will try to explain it, not only to give the definition. What do I mean? Let's consider the following example. G is a group of, any group of 2 by 2 matrices. There are many of them. For instance, you can look at, yeah, with my matrices are always with determinant 1. For integer, with integer elements, is the group with integer elements is one of the very important groups there. I mean, with integer entries. So if a group, say, is 2 by 2 matrices, a group of 2 by 2 matrices. What did I say there? What is the definition of that? You have this thing, and it may well happen that there are several lines. These are the subspaces, linear subspaces, of a two-dimensional plane, such that once you start here, and this is the only non-trivial subspace which is there. Of course, I mean non-trivial subspaces. The space is preserved by the group. Once you start here, you end up at one of these points. So if you apply any element G to this vector x, then it will be mapped on either here or there or somewhere else, but exactly here. And you can easily prove the following fact. Let's consider all matrices which have this property. This is always a subgroup. And you can easily construct such examples. For instance, you simply have a rotation there by an angle pi over something integer. And this subgroup preserves all these things. And you can make a more complicated examples of that. You can also have not just rotations, but slightly more complicated examples. I will not go into that right now, but there are plenty of them. So we want to exclude this situation, which in a sense is not very typical. It's a slightly degenerate situation, and we want to exclude it. So we introduce the notion of a strongly reducible group. This is what Furstenberg did. And I will need this condition in order to state Furstenberg's theorem. I mean, I will need this notion. Finally, the theorem. Suppose that G mu is strongly irreducible and non-compact. Then for any fixed x from S, the limit 1 over n log of the norm a of n x converges to gamma with probability 1. So we fix the initial condition, and it will always converge to the gamma which is here. the same gamma. So, 2 gamma is given by this formula, is given by formula 1. I will put a 1 here. And this is the so-called Furstenberg's formula. And does not depend on the choice of the invariant measure. You see, it may happen that there will be many of them, many invariant measures. But whatever the invariant measure, once you evaluate this integral, it will be the same number. It doesn't depend on the choice. Yes?
Give some intuition as to what you need the non-compactness for.
Well, the non-compactness I need for the third statement of this theory. Gamma is strictly larger than 0. The main thing, actually. Yes?
But can one actually prove 1 and 2 without the non-compactness?
I think yes. Yeah, I believe
Okay,
so.
maybe it's kind of trivia, yeah.
Yeah, it must be. Yeah, it's just the point is that the compact case is, in a sense, irrelevant, and that is why I don't want to put any emphasis on that. Because if it is a compact group, then, of course, this thing is simply bounded. A very interesting case from the point of view of spectral theory, but this theorem is trivial. I mean, it is not interesting. If it is, then it is 0. So what? Yes. Then it, of course, because gamma is 0, then obviously this is simply a bounded thing. So it will be 0, and and this integral will always be equal to 0. That is essentially the proof. If you have to be careful. When I say essentially, I mean essentially. No, it's very easy to make a proof of it, because if you have several points which it cannot be, you say, yeah, anyway, I don't want to go into that. Maybe a little later if we have time, but we definitely are not going to have any time. So this is the statement of this theorem. What we proved so far is the following thing. We proved the following statement, that if no measure is preserved by G mu, then gamma is positive. Now, what I want to explain now is why, and this is essentially what Furstenberg did. This is the essential part of his statement, of his proof, rather than the statement. The statement is exactly like that. This is exactly his statement. But the essential part of the proof is the one I have already explained last time, that if no measure is preserved by G mu, then gamma is positive. let me explain why these two conditions. Oh, sorry. The condition that G mu is not compact and strongly irreducible implies that no measure is preserved by G mu. So it's in a very, very abstract form at the moment, but I tend to leave this. So non-compact plus strongly reducible, these two imply that no measure on S is preserved by G mu. I will essentially prove it. It's a very short thing. I can do it. Where is this eraser? Yeah. And I will, for clarity, consider the case of two-dimensional matrices. It is a very, very easy, after I say what I'm going to say, it will be a very easy exercise to extend it to the general case. But it's a very clear thing in the case of dimension 1. Of dimension 2, sorry. Let's consider the following. So you have a non-compact group there. G mu is non-compact. Hence, you can always have a matrix, or you can have a sequence of matrices, G1, G2, and so on, in G mu, such that the norm of Gj tends to infinity. By definition of non-compactness, this is what non-compactness is. Let's consider the decomposition of Gn into these three components, which we did many times. So you have something here, un, dn, dn to the power minus 1, 0, 0, dn. What happens with this thing? How does this thing act on a unit sphere? You see, I can always think about Vn. I can choose a subsequence if necessary, because this is a bounded thing, so that Vn converges to something. So, Vn converges to V. If I then apply Gn to any vector x divided by the norm of Gnx, then except of one exceptional vector, which is such that the norm of dn minus 1 is achieved at it, whereas it is decaying, because there is always a possibility that you will have a vector such that this will be decaying. But I want, there is only one vector like that, because Vn converges to V. So if I step away from this one vector, so x is not equal to x0. X0 is something I have defined a couple of times, but here I only want to say that I will probably just remind that x0 is something which is close to x, to vector yn, such that the norm of gn yn is equal to dn to the power minus 1. They will converge by definition because I simply chose Vn so that they converge. I can always do that. It's a very general statement. Then this, of course, will also converge. Yeah, I can also consider this converging. Un converge to U. Then it is very easy to see that this vector will be, it will act essentially as following. What I will have at the end is the following thing. Let me write the result. Gn x divided by the norm of Gn x will converge to what? To the following vector. U 1, 0, 0, 0, V. X. This is the limit I will get. So every vector except on one, maybe, will converge to this one. And hence, if there is a measure preserved by all these matrices, in particular it is preserved by the sequence, it has, roughly speaking, to be concentrated on this one point. It may be concentrated also on another point, on this exceptional point. Now, if I know that this is the measure, so it is concentrated on one of these 2 points, or maybe a part of it on one of these points, the other on the other. But then it has to be these 2 points have to be preserved, because this is at the moment, these are the only possibilities to have a measure which is preserved by the whole group. I simply proved it. But then these 2 points have to be preserved. They have to be mapped into each other by the whole group. Because once a point like that is mapped to somewhere else, the measure is not preserved anymore. And this is how you prove that this condition, stronger reducibility, implies that no measure is preserved by the group. So everything is reduced to the question of the non-existence, rather, of the measure which is preserved by the whole group. And then you know that this sequence is bound. Now, I also said another thing. You see, this is a very important statement, by the way. This one is a very important statement, the first one. Once you start with a vector, you always end up, this vector will lead to a growing sequence of vectors, exponentially growing. Gamma is strictly positive, so the norm of a of n x will be of order e to the power norm a of n x will be of order e to the power gamma n. This is always like that. So I now want, why is that actually? Well, this is a slightly more sophisticated argument, but what happens is that this invariant measure, nu, has a property that it is, in a sense, continuous. It is particularly simple in the case of 2 by 2 matrices, which simply means that it cannot have atoms in its support. Once it is in the invariant measure, then due to this property of stronger reducibility, it cannot have atoms in the support. I will leave it, and I will not prove it. I'm just telling you that this is the case. And this means that also the distribution, and this is a very important statement for the spectral theory, the distribution of the vectors which are decaying, you see, there is this vector x0, which is a random thing, not at all a fixed vector. It is such that by definition we defined it so that a of n, the norm of this, is of order e to the power minus gamma f. So it's decaying. x0 is a random variable and the distribution of it doesn't have atoms. Probability x0 of omega is equal to anything, y, is 0 for every y in the S, in the sphere. It is a very important property. You know, we are talking all the time about Lyapunov exponents here. I want to make a 2-minute break in a sense that I will explain what is the meaning of this statement from the point of view of the spectral theory. So, in other words, I would like to consider an example. If I have this operator, yn, plus 1 plus qn minus energy yn minus yn minus 1 equals 0, I can always, we have done it many times, and it was discussed here many times, that this means that yn plus 1 yn can be presented in this form. It is an a1 y1 y0, where aj is given by this matrix qj minus e minus 1 1 0. So what I have said just now is what the meaning of this property is the following, that for every energy E with probability 1, there is x0 of omega such that once you start with this initial value, that if y1 y0 is x0 of omega, then yn squared plus yn plus 1 squared behaves like e to the power minus gamma n. You have a decaying solution. So on a picture, it will look like that. You start with this vector, and the norms of the vector will decay. Well, of course, they behave in a sort of complicated way, but basically they follow this line, exponentially decaying thing. The corollary of this is the following one. Suppose you consider the boundary value problem for this operator on a half line, which is y0 cosine alpha plus y1 sine alpha, or something like that, is 0. This means that what I said means the following, that for every fixed value of e, this thing will never be equal, will never satisfy this boundary condition. Because in order to have this boundary condition, that means that you have always to start with a fixed vector which is y1 is minus, so y1, y0 is always, by definition, minus cosine alpha sine alpha. It is a vector which is orthogonal to this one. Oh, sorry. No, okay. I think y1, yes, cosine and sine. This is where you start always when you solve this problem. And you want to find, now what does it mean? That means that every fixed point can never be a solution to this equation which is square integrable or summable in our case. It will grow exponentially with probability 1 for every fixed energy. So no fixed energy can belong to the point spectrum. In particular, let us think of it for a second, what it means. If I ask, what is the probability that all rational points will be in the spectrum? Or what is the probability of that? That the spectrum will be concentrated on rational points. The probability of that is obviously 0, because every fixed rational point has a 0 probability to be in the spectrum. So the spectrum we were discussing, and we very often refer to it as something which is similar to rational points. In fact, the rational points with probability 1 are never there. None of them, because each of them has a probability 0. There are countably many of them, so all of them have a probability 0 to be in the spectrum. And nevertheless, this spectrum is concentrated on some set which is reminiscent of it's a countable set of irrational numbers. This, for sure, is true. Now, this applies also to the case of double-sided thing. But then it is a corollary of one more statement from the oscillated theorem, because the oscillated theorem, which I explained here, does not only claim that there is this decaying vector, or the initial condition starting from which you will have a decaying solution to this equation. It also claims the following things, that if you go in the other direction, you consider minus 1, y minus 1, 1 minus 2, and so on, this particular solution will be growing with probability 1, exponentially. So these two guys, they never meet. Pasteur proved this statement for you in a very different way, and in a way which is much more useful than what I am saying right now. But in fact, if you are only interested in this particular statement, that the spectrum is singular with respect to the Lebesgue measure, then this is a corollary of the oscillated theorem. It's a very simple corollary of oscillated theorem. You don't need to know anything about more advanced things there. Anyway, so I just want to explain that there is some information on all these things, and in order to deal with that, or in order to understand it, you have to spend some time on it, but it's not difficult, and it is possible to understand. I think I have to move finally to the proof of the fact in order to complete the whole thing. I have to prove finally what I said last time, or what I promised to prove last time, rather. Namely, I want to prove this theorem that if no measure on a unit sphere is preserved by G mu, then the Lyapunov exponent is strictly positive. Well, it is a relatively recent thing that I found, and which is, in fact, has an easier proof than the original theorem of Fürstenberg, and at the same time, it gives a slightly more general result. And this is what I'm going to explain. But again, for that, I need one more notion. But before I do it, I'll explain what I actually want to do now. I will not suppose that everybody knows already everything I explained last time, so I will very briefly explain what I am talking about right now. So, a measure kappa of gamma is preserved by a matrix G if kappa of gamma is equal to kappa of G to the power minus 1 gamma. Gamma is a subset of S. This is what we say. Measure is preserved. That's what we call a measure kappa is preserved by a matrix G. And if this is what I had number 1 and probably 2. Okay, if I put a 3 here, this will be safe. If 3 holds for every G from G mu, then G mu preserves kappa. And we said that if no measure, so this is a theorem, if no measure is preserved by G mu, then gamma is strictly positive. That's what I stated last time. You see, of course, if I say that G mu doesn't preserve any measure, it immediately follows that G mu cannot be a compact group, because a compact group always preserves some measure. I explained last time the scheme of which allows one to prove this theorem, but I have to introduce, I did it very briefly, I will now explain it in more detailed way, but in fact, as I said, we shall prove a slightly more advanced statement, and which is easier to prove, in fact. Well, Vg of f of x is the following function by definition. It is f of gx divided by the norm of gx times 1 over the norm of gx to the power m over p. This is the definition of Vj. This is an operator in Lp of s. And what is Lp of s? Lp of s is a space. We say that f belongs to Lp of s. It is the same as to say that the integral of the absolute value of f of x to the power p over s dx, where by dx I mean the uniform distribution on a sphere normalized to 1 is 1. Oh, sorry. In this case, it is just finite. As I said, the remarkable identity I'm going to use, and which is not quite a trivial exercise, but a very, very useful one, is the following: that the norm of V j of f. So, exercise. Sorry. Is equal to the norm of f for any p larger than 1. Actually, it is also true for p equal to 1. But we will always consider p larger than 1. So if I look at this Vg of f, this means the following. I will not prove it, but I want to write it explicitly. It means the following, that if I, what is the norm of Vg of f? This is simply, I have to take this right-hand side of this thing, raise it to the power p, take the integral over s of the absolute value of f of gx divided by the norm of gx sorry, 1 over the norm of gx to the power m dx. And what I say is that this is equal to the integral over s f of x.
F to degree p.
Yes. Absolute value and p. Both. I missed them both. Thanks. And I don't think anything else is missing. It's f of g of x, absolute value to the power p. And this has to be m. This is exactly the point, that it has to be exactly m here. Dx. This is this equality. This is what here in degree p. Thanks. Of course, this is the norm of f to the power p. Yes. Thanks. Yeah. Right. As I said, if you put y equal to gx divided by the norm of gx, then you will find out that this is the Jacobian of the transformation. And it will disappear once you integrate. It's not a very straightforward calculation, but it can be done. There is also a geometric view on it, but I simply don't have the time to discuss it right now. Beautiful geometric proof, but we shall simply believe this identity. What this identity means that the norm, that Vj is, of course, it's an operator which preserves the norm, so it's a unitary operator in a sense, slightly more general than unitary, because unitary is the term which applies to the case p equals 2. But I don't care about that at the moment. Norm of Vj equals 1. So I also explained last time that in order to prove this theorem, what we actually have to prove is the following thing. We need to look at the following quantity. It is enough to show that the expectation, and I will now be accurate, with respect to s times omega. This expectation of the norm, norm of a of n x to the power minus m over p. Since I write x, and x now is a random variable belonging to this space, I will write an omega here too. So let me put it in a more accurate way. A of n omega x. Now, x is random. X belongs to S, and it is considered to be independent of omega, and that's why. So it's a direct product of measures, and omega is simply the random parameter there to the power minus m divided by p behaves like e to the power minus delta n. This is what I want. So why is that? We know the following thing, that this expectation can be presented, and I don't want to omit any indices there. Let me introduce another operator. v f of v, rather v, I will write it like this. It is the integral of vj d mu of j. I will explain what it is. V, if you have an operator which depends on a random, on a parameter, and you have a measure on a set of parameters, this is exactly what I have. I always can write something like that. Sometimes my experience shows that even very, very advanced and brilliant mathematicians, when they see it for the first time, they are slightly taken aback, because they say, okay, what do you mean? Do you mean some Bochner integral or something like that? No, this is a very simple object. Don't be frightened with it. Even though I'm talking about the operator, it is very easy to understand what I'm talking about. It is Vf of x is the following thing. I have Vj of x for every x, and I integrate it over j. This is very simple. It is the integral of Vj, for which there is a formula there, of x, of f of x. So you can simply substitute this large expression here, and then I have d mu of j. Oh, how did I write it before? Right. Now, what one has to note is the following thing, that if I want this expectation over s times omega is, in fact,
Expectation of what?
thanks, of this norm a of n omega x to the power minus m over p is equal exactly to the following thing. It is v to the power n applied to a function which is identically 1 and I have to take the norm of that on S. I hope I didn't make any mistakes. Now, how you do such a thing? This is very simple. You simply remember that the expectation of any f of a is, of let's say phi of a, is the integral of phi of a mu d mu of a of any function. If I fix x, I will have this thing. Now, here is one more idea which also belongs actually to Fürstenberg. Who made the following remark. You all might know that if you have a sequence of functions f in LP of S, or any abstract LP space, then, especially when P is 2, it is a well-known theorem that this sequence, if you have a sequence of functions Fn, then there is a subsequence of this function, of these, there exists a subsequence such that Fn converges to some f as n tends to infinity in a weak sense. In what sense? I'll explain it. I'll remind it to you. In the case of L2 space, so P for a short time will be. It simply is an element of LP. Of. No, it doesn't have to be bounded. I mean, it's LP. No, I'm trying to remind a very elementary thing. Suppose you have a Hilbert space and you have a sequence. Oh, you said Fn.
Yeah, Fn.
Normal Fn is equal to 1. Sorry. Well, what I am trying. Okay, this is a delicate way to say that I have missed a condition. Thanks. If you have a unit sphere in a Hilbert space, then it is not compact, of course, in a strong sense. But in a weak sense, it is always a compact set. So you can always choose from any, in the following sense, that if you have a sequence of functions there, or sequence of elements of an abstract Hilbert space, you have another function, say h. And you have this thing. This always converges to some f h for every h in the space in L2 of whatever, in this particular case of S. This is a remarkable fact. It's a very simple fact and a very general one. And frankly, not always very interesting. But there is a very interesting remark about it. What Furstenberg introduced is the following thing. He wants, you see, this doesn't depend. The point is that this thing doesn't depend on whether it is L2 of S or any abstract L2 space. It is an extremely general thing. And extremely general things are not very often very useful. But if you want to use an additional structure that you have the S there, then it may be very interesting. Because what is Fn of x? It is a function which has the property that this integral, say, is equal to 1. But if you now remember that every function which has this property can be considered as a density of a measure, you will also remember, you will understand immediately that if you have a sequence of such functions, you can consider another convergence there, convergence of these measures. And whereas this thing may be absolutely not interesting. For instance, if you have an orthogonal sequence of functions, it will converge, a sequence of orthogonal vectors, it will always converge to a 0. It will be converging, but to a 0. Whereas this thing will never converge to a 0. It converges to a measure which is non-trivial. And this is, of course, so I could have said it without any reference to the Hilbert space. So if you don't know anything about it, it is irrelevant. But I want to emphasize the importance of this idea that Furstenberg introduced. And then you see my R, which I erased, okay. What I want to prove is that the norm that the norm of V is less than 1, this will not exactly be true. What is sufficient to prove that the norm of V to the power k for some finite k will be 1, and then V to the power n norm of V to the power n applied to 1 will behave like e to the power minus delta n. If I have this, this is what I want to prove. So I mentioned that this is our goal, but it will follow if I have this. Now, I have to go a little further and to say that, of course, this thing for every fixed k, or for k equal 1, it is sufficient, happens if and only if the spectral radius of V to the power k is less than 1. Spectral radius. What is a spectral radius? How many people know what a spectral radius of operator is? Don't be shy and don't raise your hand if you don't know. I mean, I don't think that everybody has to know that, especially if you never dealt with that. But the spectral radius of an operator is the supremum of the absolute value of, say, lambda, supremum of those lambda, of the absolute values of lambda, such that operator V minus lambda I does not to the power minus 1 is unbounded, or it does not exist. Unbounded, say. In simple words, you have the spectrum. Okay, I can say it in a different way. It is the supremum of those absolute values of lambda, and that lambda belongs to the spectrum of V. Lambda belongs to the spectrum of V. So, since the norm of our operator is less than or equal to 1, our spectrum is inside, this is the lambda plane, it is inside the unit circle. This is the usual thing. And somewhere there is a lambda where this supremum is achieved. And if and only if the picture that the spectrum is somewhere here, anywhere here, but certainly not on the border, in this and only in this case, this thing will happen. And this is a very general theorem from the operator theory, which is relatively simple, but not entirely trivial. It actually requires some knowledge of, let me leave it here, a knowledge of complex analysis, and generally about, it has to do with some integration and some analysis which was really seriously developed many years ago by Gelfand, which was turned into the theory of normed algebras, but forget it, it doesn't matter. In principle, it is a relatively simple fact, but we shall not use it. I am mentioning it, yes?
In terms of the definition of the spectral radius, don't you have to consider the operator A star A and
No, absolutely no. No, it's a spectrum. It is simply the maximum absolute value of the spectrum, of numbers belonging to the spectrum. No. This is the spectral radius of an operator. So what Fürstenberg in fact did, and then Wirtz followed him, he proved that the spectral radius of this operator V is less than 1, but what we shall do, we shall prove that actually the norm is less than 1, and hence the spectrum, we shall go in a slightly different direction. And hence the spectrum is contained in the circle which has a radius smaller than 1. But as I said, for that I will explain the idea of the proof. And yeah, I'm afraid.
Can we open the final question session?
He's an opportunist, you see. He saw that I noticed that the watch was there, and he seized the opportunity. You know what happened to opportunists in Russia? Oh. You have no idea about that. Okay, anyway, I'm sorry. I will have to spend another 10 minutes next time to do that. I'm sorry about that. I confused everybody. Nobody has any questions. Or rather, I have explained everything so clearly that there can be no questions.
Seems that the going is tough on Mondays.
Tough, yes. To a long weekend. Okay.
Well, it's tea time. At 4 o'clock, we're having a research seminar. And then, don't forget, 5 o'clock, a big event. Phil Anderson will speak about what happened 50 years ago.